Okay, ladies and gentlemen, let's continue our discussion of integration of products by doing another integration by parts. But you'll notice in this case I have an x to the fourth. That's fine. E to the x squared. This squared is going to cause me a bit of heartache. Now, to do what I need to do to this, I'm going to still set up u, and I could set up x cubed, x to the fourth. And for dv, I could set up e to the x squared dx. I could differentiate this, no problem, but over here, to integrate this, I'm going to have to say, well, this x squared is just like a is x squared, so dA equals 2x dx, and unfortunately, I don't have an x in here to integrate with. So setting it up like this is probably not going to be the best bet. What I could do, however, is break x to the fourth into x cubed times x, allowing me to say u equals x cubed, and dv equals x e to the x squared dx, allowing me to begin differentiating here, 3x squared. And over here, I'm going to integrate, and now I have this 2 that needs to move over, and I end up with 1/2 e to the x squared, and that works out nicely. Now, if I were to integrate use my integration by parts, u times v minus integration of v du, I would say x cubed and a 1/2 e to the x squared minus integration of, and I'd move backwards, and I would have 3x squared times 1/2 e to the x squared dx, and I can't integrate that again because I have this x squared and that x squared, it's still a mess. So what I can do is, just like before, I can repeat my integration, but I can't repeat my integration of this the way it sits. But you'll notice the multiplication is what separates this when it's put back into the integration across. And if this is multiplication, the commutative property of multiplication allows me to move pieces around. So I could reshape this in this form by simply breaking up the x squared. And in fact, that's what I'm going to do. So what I'm going to do is I'm going to draw a dotted line. I'm going to steal an x from over here and put it right there. I'm going to keep the e to the x squared here, and I'm going to take that 1/2 and put it over here. So I have 3/2 x on this side, and I have x e to the x squared. The reason we have the dotted line because I did not differentiate, I did not integrate, I've simply moved bits around. So having moved my bits around, I can now differentiate. That's 3/2. I can integrate over here. That's going to be 1/2 e to the x squared. Okay, and so from here we can keep on trucking. We can keep on moving. Unfortunately, in this case, we're going to go down and down, so that's a plus, that's a minus. When I go back, it is non-integrable to this point. So I end up with 1/2 x cubed e to the x squared minus 3/2 x times another 1/2 e to the x squared, sorry, minus plus minus plus the integration of 3/4 e to the x squared dx. Now, at this point you say, well, you can't integrate that anymore. No, I can't. But I have broken down a more complicated problem into a more simple problem, so that if this were a subsection of a larger issue, this would get me worked out part of the way and hopefully far enough that we could finish the problem off. If this were an x to the fifth, we would have gone with a fourth, and then that fourth to a cube, and that cube to a squared, and that squared to an individual value, and then it would have worked back across. So it all depends on what this exponent is here and what the substitution is here. So the redistribution allows us to stop part way and move bits around. Now, that's not the only way that we can move bits around when we have things left over. If we were to deal with the integration of cosine squared theta d theta. Now, in this particular case, we have another issue. Cosine is easy enough to integrate, but this squared is a problem. So what we're going to need to do is we're going to use integration by parts. Unfortunately, we don't have a lot of parts to work with, so the best thing I can do is split this up into two pieces. By splitting it into two pieces, I can say u equals cosine theta, dv equals cosine theta d theta, and I can integrate. All right, so derivate here, I get negative sine theta. Here I'm going to get, to integrate this is going to be positive sine theta. And so when I multiply down, I come up with cosine theta, sine theta. Go backwards, and I get minus a negative sine squared theta d theta. And you say, well, that's no good because I still can't integrate this. All right, fine. Let's not go back yet. Let's go ahead and integrate and differentiate again. In this case, negative sine turns into a negative cosine theta. Integrate this sine again, and I get a negative cosine theta. And so now we're going to go down once, down twice with the minus, and now try going back with the plus. So we come up with cosine theta, sine theta. Now we have down as a minus, but I have two negatives. Those go away. So minus multiplication of negative sine theta times negative cosine theta. And then we're going to go back across with a plus integration of negative cosine theta squared d theta. In this case, we come up with cosine theta sine theta. Two negatives go away, minus sine theta cosine theta. And we end up with a plus cosine theta.